Hi everyone. In this video I am going to explain the algorithm to count number of bits required to represent the given decimal integer in a binary. Let us understand this by taking one example. Let us take some n number in decimal integer. So let us take n is equal to 19. Okay, now this is in what? Decimal number system, 19. So now, first of all, we need to convert that decimal number into a binary number. How to convert? So simply keep dividing the number by 2, okay, until the number becomes 1. Whenever the number becomes 1, we need to stop. When we divide 19 by 2, 2 9s are 18 and 1 is the remainder. Again the number is not 1, the number is right now 9. So again divide the number by 2, so 2 4s are 8, again the remainder is 1. Again the number is still not 1, so again I am dividing the by 2. So 2 2s are 4, remainder is 0. So again the number is not 1, so again I will continue dividing. 2 1s are 2, remainder is 0. Now the number becomes 1, so now I will stop. Once we stop, so now we need to write it in the binary form. That means the number 19 in decimal number is written in the form of binary 10011. This is in the form of binary. Now to represent the number given decimal integer 19 in binary, we need how many bits? 1, 2, 3, 4, 5. So the answer is 5. So this is what we need to do. So that means, so in order to represent the given decimal integer in binary, we need how many bits? Okay, so we need 1, 2, 3, 4, 5 bits. 5 bits we need to represent decimal integer 19 to represent in binary. This is what we need to do. Now let us say, suppose the minimum number what we have to take is minimum number is 1. Okay, minimum number what we have to take is number 1. This is in decimal number. This is in decimal. Okay, this is in binary. So number 1 in decimal, same thing can be written in binary also 1. So the minimum number of bits to represent the minimum number is again 1. Suppose if number is 2, so then in binary we need again 2 bits. So number of, okay, now in binary we can write same thing as 0 and 1. Sorry, this is 1 and 0. 1 0, this is binary 2. So we need 2 bits. Okay, so to represent 3, so we need to represent in binary is 1 1, and again we need 2 bits. Similarly for 4, we need 1 0 0, this is a 4, we need 3 bits. So minimum number of bits we require is 1. If n is equal to 1, we need 1 bit. Suppose if n is greater than 1, we don't know how many bits, but greater than 1. Suppose that means if n is equal to 1, so conclusion is what? If n is equal to 1, we need 1 bit. Suppose if n is greater than 1, obviously we need more than 1 bit, but we don't know how many. That we need to calculate. So for that what we did, we keep dividing the number by 2 until the number becomes 1. When the number becomes 1, we stop. Okay, this is what we did. So for this now we'll write the algorithm. So I am taking the name of the algorithm binary underscore bits. This is the given number for which we need to find. So we know initial condition what? If n is equal to 1, then we need number of ones. But if greater than 1, what we have to do? If greater than 1, we have to divide. If greater than 1, divide it. Greater than 1, we divide it. Greater than 1, we divide it. When greater than 1, divide. When we not divide it. So if it is 1, the number of bits required is 1. So otherwise we have to divide. Okay. So now I have to check if n is equal to 1, then what we have to do? Then we need to return 1. That means we need only 1 bit to represent that. Else, if n is not equal to 1, what we have to do? We need to return what? Again I am calling the same function. So that is binary underscore bits. But now I am not calling again. See, first time I need to calculate for the 19. Next time for 9, that is half. So that is n by 2, and I am taking the lower limit. That means when we divide, so I'll get, see, 19 by 2 is what? 9.5, but I'm taking the lower limit 9. Similarly, when divided by 9 divided by 2 is 4.5 actually, but I'm taking lower limit 4. Okay, so this is the symbol for to take the lower limit. So plus 1 bit we need. Okay, so this is what the algorithm for to find the number of bits required to represent the given decimal in binary. Now let us take the same example to trace the algorithm. First, binary underscore bits. First I'm passing 9, the given n. Now 19 is equal to 1 false, comes to the else part. Now it returns binary bits of 19 by 2. I'm taking the lower limit. 19 by 2 is what? 9.5, but I'm taking the lower limit, so 9. So 9. So again, this function is calling itself. Again, now again, if 9 is equal to 1, false comes to the else part. Now it is calling through 9 by 2 plus 1. That is 9 by 2, lower limit is 4. So 4. 4 is equal to 1, again false, return binary bits 4 by 2. 4 by 2 is now what? 2. Okay, now 2. 2 is equal to 1, false, again binary bits of 2 by 2 is 1. So binary bits, here 1 we are calling. If now here 1 is equal to 1, yes, 1 is equal to 1, true. Now the condition becomes true. Now comes inside, return once. Return once. Now it return 1 to its caller. That means in this place, it returns 1. Okay, it returns 1. So here plus 1. So this plus 1 plus 1, 2. Now it returns 2 to in its place. In this place, it returns 2. Now this will be replaced by what? 2. So this is plus 1. Okay, plus 1 is 3. Now 3 will be returned to in this place. So now this will be replaced by 3. 3 plus 1 is 4. 4 is replaced in this position. Now this is 4. 4 plus 1 is what? 5. So it returns 5 to its function. So now finally we need 5 bits to represent the given decimal number 19. So this is how this algorithm works. Hope people understood. Now let us see how to do analysis. The analysis, what is the first step? So we need to find the problems. What is the problem size? For the given number, we need to find. So the given number n is the problem size. So n will be the problem size. Now, next, what is the basic operation here? So here basic operation, actually what we did, after finding in the binary, what we did, we counted 1, 2, 3, 4, 5. Similarly, what we did, see here we are counting 1. See, 1 plus 1, 2. 2 plus 1, 3. 3 plus 1, 4. 4 plus 1, 5. So here addition operation is the basic operation. So addition operation is the basic operation. Next, third step, we need to decide whether we need to find all the 3 cases or only average case. In this case, it depends only on the number what we are giving. Okay, so we need to find only the average case big theta. So now fourth step, we need to represent how many times this basic operation, that is addition, is executing in terms of recursive function or recursive equation. So now since addition operation is the basic operation, I am taking a of n. Okay, a of n is equal to what? Now see, a function calling itself by its half. Actually, the function of parameters n, this itself calling itself by n by 2 plus 1. Similarly, this is a function calling itself with half plus 1. Again, I'll repeat. A function calls itself with its half plus 1. Similarly, a function call itself with its half. So, a of n by 2 plus 1. Okay, function call itself. Function call itself. Okay, function call itself. So function call itself with half. Function call itself with half. Plus 1 plus 1. Okay. So this is our recursive equation. So what is the initial condition? Initial condition, we know that if n is equal to 1, 1. So a of 1 is equal to 1. That means if number of the decimal integer is 1, then number of bit required is only 1. So this is the initial condition. Now in the fifth step, what? We need to solve this one. Okay. So for solving, so now again I will rewrite. So a of n is equal to a of n by 2. Again here also we will use backward substitution method to solve the recursive equation. Okay. So now a function is equal to its half plus 1. So now a of n by 2 is equal to what? A function of this one is its half plus 1. So I will write this as an a of n by 4 plus 1. Then plus 1. So this plus 1 as it is. Now in this place I replace. So this is nothing but this one. Okay. A function is equal to a function of its half. N by 2. Half of is 1 by 4. So this I will write it as a of n by 2 square. Instead of writing 4 I am writing 2 square. Plus 1 plus 1 I am writing 2. Now a function is equal to its half plus 1. So I will write in this one as a of n by 8. 8 I am writing as 2 to the power of 3 plus 2 plus 1, 3. Okay, similarly it goes on. So finally I will write it as a of n is equal to a of n by 2 to the power of I plus I will call this equation 1. But what we know that what? We know that only what? A of 1 is equal to 1. So we need to make this term as 1. So for that what you have to do? Put what? 2 to the power of I is equal to n in equation 1. If I put 2 to the power of I is equal to n, so both numerator and denominator becomes 1, cancel, then it becomes a of 1. If a of 1, I can easily replace by 1. So I am putting 2 to the power of I is equal to n. So the equation 1 becomes a of n is equal to a of n by n plus I only. So now n get cancelled. Now a of 1 plus I. A of 1 is equal to 1. So this is 1 plus I. Now, but again, I will call this equation. Again, we don't know I. But we replace 2 to the power of n. So apply log 2 on both sides. On both sides. Now what happens? So log 2 to the power of I to the base 2 is equal to log n to the base 2. Now take I outside. Now I log 2 to the base 2 is equal to log n to the base 2. Now when these two are same, values becomes 1. So I is equal to log n to the base 2. So I got the value of I. So now I replace the value of I in the equation 2. So a of n is equal to 1 plus log n to the base 2. Now out of these two terminologies, we having most dominant term is log n. So I will write a of n belongs to big theta of log n to the base 2. Now this is your time complexity of this problem. Hope you people understood. Thank you.